Hello my dear friends, hope all of you are doing well by keeping yourself safe. Please try to maintain proper COVID protocol every time while going out. So today in this video I am going to discuss a new concept like on the dielectrics and the phenomenon called polarization. So without any further delay, let's begin. So dielectrics and the polarization. So the word dielectrics seems new to us, but the material is not quite different. It is mostly the insulator material. Dielectrics are mostly the non-conducting substances sometimes it is also called the insulators, and having no or very negligible number of charges carriers are present. It means it has either no or very negligible amount of charge carriers. It means the electrons. So you can see that in dielectrics the electrons are tightly bound to their parent atom or molecules, and there are no free charges. So as I have discussed that there are no free charges and the electrons are tightly bound to their parent atom or molecules, and it is mostly the non-metallic substances having high resistance and may have induced dipole moment in the presence of external electric field. So while I put the dielectric material in the external electric field, there will be induced dipole moment generates. So, and mostly it is used to store the electrical energy. Such example of the dielectrics are like mica, glass, plastic, and the water is also a dielectric material or liquid. So in case of conductor, we can see that the charges are free to move through the materials, but as I have already told that in the case of dielectrics, we can see that the charges are attached to some specific atoms or molecules. This type of charges we can call it the bound charge. Under the influence of some external electric field, if we put some external electric field, we can see that the bound charges are able to displace within the atoms or molecule, and such microscopic displacement are not like as what we can see in the conductor. So it is quite different, and then the movement of the bound charge is quite different in the presence of the external electric field in the case of the dielectrics. So this is called the dielectric polarization, is the displacement of the charged particles under the action of the external electric field. So several microscopic mechanisms are responsible. You can see in the absence of any external electric field, you can see there is the dipole moments are there. So dipole moments are randomly aligned, so the dielectric has no net dipole moment, and in the presence of the electric field, you can see that under external electric field E, this is the direction of the electric field. So the dipole moments will align in the along the parallel direction of the electric field. So the electron will go in the opposite direction of the electric field, and the positive charge will go in the direction of the electric field. So it is called the polarization. So there are several kind of microscopic mechanisms are possible in the case of dielectric polarization. One is electronic polarization, one is ionic polarization, another one is orientational polarization, and the last one is interfacial or space charge polarization. So we can see that in the presence of the external electric field, the dielectric material, there is a shift of the center of positive and negative charge, you can see, and for this reason each atom or molecule acquires a dipole moment. This property of the dielectric is known as the polarizability. So I can write that under external electric field, the positive and the negative charges of atoms or molecules inside the dielectrics are displaced in a direction opposite to one another. So the electron will move in the opposite direction of the applied electric field, and the positive charge or the nucleus will move in the direction of the applied electric field. So their center of the center of the charges will get separated. So we can write that, and this effect is to pull the opposite charges apart to polarize the molecule. So in this scenario the molecule will get polarized. So for each generated dipole moment, we can write that it is called the induced dipole moment because it get introduced in the presence of the external electric field. So for each generated a small dipole moment, induced dipole moment, small p vector of an atom or a molecule, because there is a separation of the positive and the negative charges, we can write that the small p vector, the induced dipole moment, is proportional to the localized electric field acting on the atom or the molecule. So, and the proportionality constant is called the atomic polarizability or the alpha. So this is the atomic polarizability, and the induced dipole moment is proportional to the applied local electric field. So we can say that the dipole moment is proportional to the local value of the applied electric field acting on that atom or the molecule, and the process is called dielectric polarization. I have already discussed. So now we can see different type of polarization process. The first one is the electronic polarization. So you can see from the figure I have drawn here that the electronic polarization, it happens due to the displacement of the positively charged nucleus and the negatively charged electron cloud in the opposite direction. So it mostly happens in the case of the atoms. You can see atoms has a central core is called the nucleus, and outside there is electron cloud, because electron, there is a probability density comes out in the chance of finding the electron in some specific space. So we are assuming the electron to be as a cloud. Now in the presence of the, in the absence of the electric field, it behaves like this, but in the presence of the electric field, you can see the electric field is acting from the right to left. So the electron will move from left to right. So you can see that this is the initial position, and the electron gets shifted along the direction of the electric field, and the electron cloud will get shifted in the opposite direction of the electric field. So there will be a separation of the there will be net resultant separation between the nucleus and the electron cloud. So this happens for this atoms, and it occurs in the optical frequency range of 10 to the 15 Hz. So this is one kind of polarization process is called the electronic polarization. The next one will be like ionic polarization. It happens in ionic solids due to the displacement of the positive and the negative ions. As we all know, the ionic solids is made up of different, one is cation, another one is anion. So it is the ionic polarization is it happens due to the displacement of the positive ion or the cation or the negative ion or the anion in opposite direction. As like before, we can see that the negative ion will get displaced in the opposite direction of the electric field, and the positive ion will get displaced in the along the same direction of the applied electric field. Like NaCl molecule, Na plus Cl minus, it is a ionic molecule in the frequency range of 10 to the 13 Hz. This molecule gets separated. So initially, suppose from this figure you can see this is the initial distance between Na plus and Cl minus, it is R0, and with the application of the electric field, like the final distance in between Na plus and Cl minus will be R0 plus x, where x is the change in distance in between the Na plus and Cl minus atom or ion, you can better to say. So the polarizing power of the positive and the negative ion depends on their size and the charge. It depends on the size and on the charge of the cation and the anion. So our next page is like, so we can see that from the up to now that the NaCl is an ionic crystal, and where the ionic polarization can occur, so there will be an increase in the separation between Na plus and the Cl minus when there is it is because it is an ionic molecule and different amount of ionic charges, like, so we have different kind of ionic molecule, like where the ions have different charges, like calcium fluoride. So for that case, the ionic polarizability calculation is more and more complicated. So like previous discussion, for this Na plus Cl minus, you can see that Na plus and Cl minus both have the 1 unit of positive charge and 1 unit of negative charge, but in some molecule like calcium fluoride, there is different unit of positive and negative charge. So the calculation of the ionic polarizability is quite different and complicated. So our next discussion will be like orientation polarization. So this kind of polarization are present in the polar substances which have permanent dipole moment in the absence of the external electric field also. So we will discuss in this later video that what is polar molecule. Due to the random orientation of the dipoles or the molecules, the net dipole moment is 0 initially, because there is no external electric field is there, the net dipole moment is 0. So it occurs in polar substances which have permanent dipole moment in the absence of the electric field. The polar substances, they have the permanent dipole moment in the absence of the electric field. In the absence of electric field, the net dipole moment is 0. You can see here, there is dipole moment is 0, but for the material, for the whole material, the net dipole moment is 0. So if we put some external electric field, there is some resultant dipole moment exists, because all the dipole will tend to align in the direction of the external electric field. So in the absence of electric field, the net dipole moment is 0. In the presence of external electric field, the dipole moments are tend to align in such a way to give rise to enormous dipole moment. And this kind of polarization occurs at a frequency range of 10 to the 6 to 10 to the 10 Hz, and it is slow compared to the ionic polarization. So you can see this is a dipole, and in the presence of the external electric field, the positive charge will, positive and the negative charge, or ion better to say, will feel the force in the opposite direction. So there will be torque, and the torque will tends to align the dipole in the direction of the external electric field. So this kind of polarization is called the orientation polarization. And the next one will be like interfacial or the space charge polarization. So this kind of polarization occurs when there is accumulation of charge at the interface. Suppose we placed one dielectric material in between two electrodes. So you can see I placed here one dielectric material in between two electrodes, and then there is different, and it is different from this kind of interfacial, and the space charge polarization is different from orientational and this ionic polarization that we have discussed before, because in this kind of polarization like interfacial or the space charge polarization, there is also free charges are involved with the bound positive and the negative charges. So in this kind of interfacial and space charge polarization, I repeat again, here we will deal with the bound positive and the negative charges along with the free charges like the electrons, but in the case of orientational and the ionic polarization, we dealt with only with the bound positive and the negative charges. So the accumulation of charge at the interface because of the external field, you can see from the figure, this is the direction of the external field. So the positive charge will get accumulated at this surface, and the negative charge will get accumulated in this surface. Also, in parallel to both bound positive and negative charges, there will be movement of the free charge carriers, which is the electron. So this is the difference of the interface, the difference in between interfacial or the space charge polarization along with orientational and the ionic polarization. Remind that. And also different from electronic and ionic polarization, because this kind of polarization also affects the free charges inside, as we have already discussed. So now you can see that also the interfacial and the space charge polarization mostly observed in amorphous and the polycrystalline materials. So we can already understand that due to the presence of the electric field, there will be a charge imbalance due to the dielectric materials insulating properties in the case of interfacial polarization. However, in the case of interfacial polarization, we have already seen that the mobile charges like the free electrons in the dielectric will migrate to maintain the charge neutrality, causing the interfacial polarization. So from this figure you can see that there will be the movement of the bound positive and negative charges. Along with them there will be movement of the, I have not depicted here the movement of the electrons or the free charge carriers, but in the case of interfacial or the space charge polarization, there will be movement of the bound charges along with the free charge carriers like electron. So now we'll try to understand one important phenomenon, and I will try to find the behavior of one conductor and one dielectric material when they are placed in an external electric field. So the behavior of conductor and the one dielectric material when they are placed in an external electric field. So you can see from the figure, this is the external electric field E0, and I have placed one conductor here in the left side, and this is one dielectric in the right side. So from this figure you can see that when the conductor is placed here, the free electron will move in the opposite direction of the field. The free electron will move in the opposite direction. This is the property of the electron, and there will be one induced electric dipole because the electron will move in this direction and the positive charge will move in along the direction of the electric field. So there will be induced one electric field inside the material, inside the conductor better to say. So this is the direction of the E0 external electric field, and this is the induced electric field that is inside. So you can see both are the same in magnitude but the opposite in direction. So for the conductor we can write that E0 is equal to minus of E in. So the net electric field inside the conductor is 0. But in the case of dielectrics, now you can see the right figure. There is no free carriers in the dielectric, and the dipole moment will be induced in the molecules of the dielectric. The induced opposing field is not strong enough. The induced opposite field, the E in, is not strong enough such that it will cancel the external electric field E0. So there will be a reduced value of the electric field inside the dielectric. It means the sum of the E0 plus E in is not equal to 0, and the net field inside the dielectrics, what it will be? E0 minus E in. So this is the net field inside the dielectric, because E0 is not equal to E in, and E in is and the value of the E in is just to suppress the external electric field E0 inside the dielectrics. So now, so far we have seen that the different kind of polarization process that are there when we apply some external electric field for the dielectric. There will be dipole moment generated for the atoms or molecules when they are placed in the field. So some molecules have an unequal sharing of the electrons in a bond are called the polar molecules. So when there is unequal sharing of the electrons, it is called the polar molecule. They have a permanent dipole moment. The polar molecule have a permanent dipole moment irrespective of the presence of the field. But sometimes there are molecules, they don't have the unequal sharing, or better to say they have the equal sharing of the electrons. So they are called the non-polar molecules, and they don't possess any permanent dipole moment unless they are placed in any external electric field. So for the, let's see what is the definitions of the polar and non-polar molecules. So you can see this is a polar molecule. The HF is a polar molecule. You can see at the F, on the F atom there is 3 lone pairs. So this F is more electronegative than the H atom. So F atom just drag the electron of the bond to its nearer point. So this side will get slightly negative charge delta minus, and this side of the H atom will get slightly positive charge delta plus. So it will behave like electric dipole on the magnetic pole, because there is difference in between positive and a negative charge, and they are separated at a distance. So the polar molecule has the property they are mostly asymmetric, bent or trigonal pyramid shaped molecules. So this kind of structure they have, the polar molecule, and lone pair of electrons on central atom, or having atoms with different electronegativities bonded. So you can see the H and have their different electronegativity, and the difference in electronegativity is quite high, up to 0.5 to 1.9. So you can see for the water molecule O, the oxygen has a lone pair, 2 lone pair, and this side is delta plus, this side is delta minus. This hydrogen, because oxygen is more electronegative than hydrogen, similarly this side also delta plus, so it becomes 2 delta minus. And the polarity acts from H side to O, so this is the direction of the polarity, and the net polarity is acting in this direction. So H2 has a net polarity, it means H2 has a polar molecule, H2 is a polar molecule. Similarly, like NH3, you can see in the central N atom has 1 lone pair, it means 2 electrons, and this is the direction. So N is more electronegative than of hydrogen atom. So this is the direction of the polarity, and the net polarity acting in this upward direction. So NH3, H2 and HF all are the polar molecule. So our next discussion will be on the non-polar molecule. So this is the non-polar molecule. So I have already written here, for the polar molecule, one end of the molecule becomes slightly positive and the other end becomes slightly negative. Polar molecules have molecular structure such that the sum of the vectors of each bond dipole moments do not cancel. So you can see from the figure that from this following the previous figure. So this is the figure. So in this NH3, you can see this polarity direction is this direction, this in this direction, this in this direction. So the resultant polarity acting in such a way that the resultant is not 0. So for the polar molecule, the sum of the vectors of each bond dipole moments do not cancel. Similarly, what is the non-polar molecule? The molecules must be symmetric. for the nonpolar molecule, the molecules must be symmetric and all of the sides around the central atom are identical and bonded to the same element with no unshared pair of electrons. So there is the electronegativity difference is not very large, and the electronegativity difference between the bonding atoms are very small. The difference is up to 0 to 1.4. So you can see this is the CO2 molecule. This is the direction of the polarity. There is the presence of the polarity, but the resultant polarity is 0, because if you try to find the resultant of these two polarity direction, you can find it is 0. So the CO2 is a non-polar molecule. So you can see that the oxygen is more electronegative than carbon, so it gets minus polarity here, and this is the direction of the polarity, and this is the direction of the polarity in this side. So the resultant of the polarity direction is 0. So CO2 is a non-polar molecule. Like hydrogen, chlorine and oxygen, both all are the non-polar molecule. So now we will discuss that if we place one dielectric bar inside the electric field, so we can find that there is the in between the two charge electrodes, if we put some dielectric bar, so there will be local induced dipole moment, as we have already learned, and it is equal to the applied, it is proportional to the in dielectrics, the induced dipole moment P is proportional to the local electric field. So this is for the each atom or the molecules, and we define one position, the vector P, capital P, as the dipole moment per unit volume is called the polarization vector. So the capital P, we can write it like in the form of summation capital P vector is equal to sum over I to n pi vector divided by whole volume of the dielectric. So this is called the polarization vector. So we can write that the polarization vector capital P is proportional to the total flux density and acts towards the direction of the electric field. So we can also find the relation that capital P vector is equal to epsilon naught chi e. So what is chi e? Chi e is called the electrical susceptibility, and epsilon naught we know that it is the permittivity of the vacuum. So as I have already discussed that the chi is called the electrical susceptibility. So now you can see from this figure here, this is the dielectric bar I put in the external electric field capital E acting in this direction from left to right. So the bound charge will get aligned in such a way that this is the dipole, there will be some generated induced dipole moment, and all the dipole moments will get aligned in the direction of the electric field. So you can see inside the dielectric bar, this plus, this minus, this plus, this minus will get cancelled, but in the surface, this for this negative charge there is no positive charge, so it will not cancel. So this side of the dielectric bar will get negative charge and this side of the dielectric bar will get positive charge. So this type of polarization is called the uniform polarization. And for uniform polarization, what I have already discussed, that the volume charge density for the bound charge rho b is equal to 0, because inside the dielectric bar there is no charge, but the charge exists in the surface of the dielectric bar in the both sides, but the surface charge density for the bound charge sigma b is not equal to 0. So I hope you are understanding what I am telling. So the volume charge density for the bound charge rho b not equal to 0, because there is surface, at the surface there is a charge there, but inside the dielectric bar in the whole volume the charge is 0. But for the non-uniform polarization, I will say that both the volume charge density for the bound charge rho b and the surface charge density for the bound charge sigma b exists, because here the dipole moments, all the dipole moments are not parallelly aligned in the direction of the electric field. So this is the difference of the uniform polarization and the non-uniform dielectric polarization. So you don't need, you just may know this relation between the rho sigma b and the rho b with the polarization vector. This is not in your syllabus, that sigma b is equal to p vector dot n cap and rho b is equal to minus of gradient of p. So this is the n cap is the normal to the surface, and rho is the gradient is a vector, so we can write it like del del x I cap plus del del y of j cap plus del del z of k cap. Now the electric displacement vector is a quantity, so we will define that for the dielectric material, in the presence of the external electric field, the bound charges in the material slightly separates, inducing local dipole moment, and we can define the displacement vector D as equal to epsilon naught capital E vector, the external electric field, plus the polarization vector. So it comes out to be epsilon naught E plus, if we put the polarization vector relation with the external electric field, we can see from our previous discussion that it is epsilon naught chi E. So if we put the value here, we can see that it comes out to be epsilon naught E plus epsilon naught chi E times E. So it comes out to be epsilon naught epsilon R capital E. So we define that epsilon R is equal to 1 plus chi E. So now epsilon naught epsilon R, we define it as epsilon, so D comes out to be epsilon E. So comparing epsilon is equal to epsilon naught epsilon R, so this quantity epsilon R comes out to be epsilon by epsilon naught. This is the permittivity of the dielectric medium divided by the permittivity of the vacuum. So this is called the relative permittivity of the dielectric material, or the dielectric constant. So this is one fundamental quantity for the dielectric, or the measurable quantity for the dielectric. So we must say that a limited shifting of the electric component that occurs when we apply an external electric field, or we can remove the external electric field, then the corresponding current is represented by the displacement vector. This is the relation of the displacement vector and the polarization vector. So in other words, we can say that the displacement vector is a charge per unit area that would be displaced when a conductor or a dielectric is placed in an electric field. It is also known as the electric flux density. It means the charge per unit area, the displacement vector. So my friends, I am concluding my discussion here. For now, if you are facing any kind of difficulties, don't hesitate to let me know in this video's comment box. I will be happy to help you. Stay tuned and keep supporting Invisible Threads. Stay safe and thank you.